We are on pretty much chapter 5. All right? That's what we're looking at.
We did few post answers of it.
The last what?
The last slide that we handed in.
The one with the simulation of pushing and pulling.
Yeah.
I don't ever put lab solutions on there, but if you want, I can put the blank lab on there so you can see the kind of questions you'd expect from that. Because I still have your lab for that. Yeah. But I can put a blank lab on there, and if you're like, oh, I couldn't get number 8, I wasn't really sure when I did it, you're happy to ask me. That's fine. You feel free to ask me, is what I'm saying. So chapter 5, right? In the beginning of chapter 5, we started by talking about Newton's 3 laws. Can we talk about maybe one of the 3? Give me something. Give me one of Newton's 3. Yeah. So an action has an equal but opposite reaction. Okay, Newton's law. That's technically Newton's 3rd law. The order does not matter, so I'm not concerned about 1, 2, 3. Okay, that's one of Newton's 3 laws. Every action has an equal and opposite reaction. Yeah, that law can be summarized as the law of inertia. So another one of Newton's laws was the law of inertia. Okay, and inertia told us if an object is moving, it wants to stay moving. If it's at rest, it wants to stay at rest. It's an object's desire to remain in its current state. Current state being motion or not motion. What prevents an object from staying in its current state? What prevents it?
Friction or force?
Yeah, some sort of outside force. An example that is he gave friction is a good example. Friction is a good example of something that keeps an object from its current state of motion. So if I push this object, it stops because friction is causing it to slow down. It wants to keep moving at the rate at which I propelled it forward, but it's not going to do that. So inertia is only affected by an outside force. And then what's the 3rd law? Or not the 3rd law, but what is the 3rd of the 3 that we haven't named? F equals ma. Okay, and more specifically, we say the sum of the forces. So we can put that big symbol there, right? This means sum. If you recall, I also mentioned the fact that the word net is used here. You might say F net equals ma. And net simply means the sum of net and ET means the overall force is acting. So whether you read it like that, or if you read it like this, it's the exact same law. And you could write it or see it either way. Now, this 3rd law was the most important, as you noticed, right? We're using it in every single problem. Mathematically, the 3rd law is what derives, or what pretty much gives us all our equations of motion. If we want to look at an object that's undergoing some sort of force or accelerated push, we use this. Now, how many directions do we use this law in? Is it just a general law like this we write it, or do we specify a little further? What have we been doing in class? Yeah, it depends on the problem, but we look at the x and the y direction for this as well. So we remember that this law is applicable in both the x direction and in the y direction. And remember that a could be 0 in certain circumstances. It's not always 0, right? I could have a vertical acceleration with the elevator example. Remember the elevator example? That could be vertical acceleration. So that's a value, or that's a problem where ay has some value. I could have horizontal acceleration like you saw pretty much in all of the problem sets, right? Those problem set questions, a lot of them involve figuring out the acceleration from VF and VI and T, or VF and VI and X, finding acceleration, and then using that in the X direction. Or there could be no acceleration, and we're either not moving, or we have a constant velocity. So the problems that involve constant velocity or no motion at all talk about where acceleration is equal to 0 in those problems. Okay? So a lot of the time we're going to notice that the right-hand side of the equation over here, or the right-hand side over here, might go to 0, or might turn out to be 0 on the right-hand side. How about the left-hand side? Can somebody explain in their own words what takes the place of this sum of the forces? What takes the place of the sum of the forces in both the x and the y direction? And I'm not asking for the exact forces. I'm saying generally, how do you replace this? What do you use to replace this value?
You use mu times
So it depends if we're going to use mu. Mu will be used if we're working about friction, right? For friction specifically. And applied force is used if there is an applied force. Sometimes there's not applied force though. Like the track runner, it was only static friction. I was pushing him or her forward. It wasn't the applied force, it was static friction. So for these problems, I'm asking generally, Julian, where do I get my information to replace this with stuff? And replace this with stuff?
So for the y, it's FA minus FG.
A lot of the time it is, right? So give me more general of an answer, even more general than that, Kim. Where am I looking to get those forces? What do I draw to get those forces? What do I draw for all problems to get those forces? Yeah, a free body diagram. Good, that's what I was getting at. So my free body diagram is what gives me what substitutes in for those two underlying values there. If I've got three forces acting in the x direction, I'm going to replace this right here, some of the force in the x, with those three forces. If two are to the right, well then two of them are positive. If one is to the left, then one is negative. So it really depends on my free body diagram. So I'm going to give you a free body diagram at the top right now without any problem at all. Okay, no problem whatsoever given. I'm not going to give any words to it. I'm just going to draw a free body diagram. And from that diagram alone, I want you to just practice coming up with the two equations you're going to have. So let's say that this is my object right here. Let's say there's an applied force in the x. There is tension in the y. There is the weight pulling down. And maybe this is going down a ramp or something like that. Or actually, I don't want to go crazy. For now, let's say friction is acting backward. And we'll say that this object is undergoing static friction. So all I would do for any diagram, I'm starting with a simple one, right? With an applied force only in one direction. With tension acting upward. With the weight pulling down. With friction pulling back. So maybe that friction force there, maybe that friction force itself is between a table, or maybe it's actually like an object suspended from a cable in the area system. I don't care. I'm not even concerned with the problem, is what I'm saying. But based on the diagram alone, you should be able to come up with your two equations here. Now, what else would you need? What other piece of information would you need? Besides the forces, what else do you need to know about the problem? Joe? Yeah, whether or not it's accelerating. Good. If it's accelerating, then we're going to put a number in here. If it's not, if it's either stationary or constant velocity, these both go to 0. So for now, we don't know what's happening there. But what would that look like in the x direction? What will my equation be in the x direction for this? Huh? FFS is in the left direction, so what should I do with that?
Minus.
Yeah. So a negative FFS, because it's pointing left. FA is pointing to the right, so that's positive. And that equals MA. Now remember, the order could be different. If you wrote FA minus FFS, that's the same thing, right? So you can switch the order of these two as long as you remember to carry over the negative for FFS, wherever it is. How about the y direction? How about the y direction? What is in this diagram, remember, so it's not the same for all answers. It depends on the scenario. In this diagram, what would the equation be in the y direction? FG is acting down, FT is acting up, and that equals MAY. And again, maybe there's no acceleration. I don't know. So we have to give that information as well. But I want you to see that the free body diagram gives everything. It gives everything. Now, beyond that, beyond the free body diagram, as I think Julia mentioned a little while ago, we have to also consider the fact that friction is defined as mu Fn. Well, in this case, there's no Fn in this problem. Do you see that? There's no Fn in the y direction. So this frictional force here is probably like an air resistance more than it is a surface contact. And you might say like, oh, well, the friction from the air is -12, so that just becomes -12 right here. So that's a formula that we sometimes use. And then the other formula that we always use is this one right here. So the two formulas in red become substitutions we might make in our equation based on what we're given. So for example, if I said the following, listen carefully to this. If I said that the weight of the object was 15 newtons, The weight of the object was 15 newtons. Where does that go in this problem? Where does 15 newtons go? What variable is weight? What variable is the weight of an object?
15 times 9.8.
You're on the right track if it was given as mass. If I told you it was 15 kilograms, the mass of the object, you would do that. But if you're told that it's just 15 newtons, this is a little bit different. If the weight itself is 15 newtons, what is that variable? It's the weight. That's the actual force. So this right here would be negative, because the negative is here, right? 15 newtons. The whole thing would be 15 newtons. But, Chinmay, to follow up, this is what I was going to ask afterward. If you were told that the mass is 10 kilograms, right? Newtons versus kilograms, that's how I know which one I'm given. If the mass is 10 kilograms, then you have to do 10 times 9.81, and then you put a 98.1 here with the negative sign carried. So if you're given the mass of an object, and you have to use this in the formula, you got to multiply by 9.81. But if you're given the actual weight of an object, then you have Fg. That's what Fg is defined as. Fg is the weight of the object. So if you're told that an object has a weight of 15 newtons, you literally plug in 15 for Fg right there. How would I figure out the mass of an object if I'm told the weight? If I'm told the weight, how would I figure it out, Joe?
Would you divide it by 9.81?
Good job, Joe. Well done. So we notice here that if you're given the mass, you multiply by 9.81 to get the weight. But if you're given the weight, you got to get rid of g now, right? So you would divide by g. So if you're given the weight, divide by 9.81, isolate the mass. And how do I know that? Just solve that formula, right? Take a look at this formula and solve it for mass. Mass is equivalent to the weight of the object over the gravitational constant. Now remember that this g is not a variable. This is not a variable. This is a subscript here. So this represents the force due to gravity, aka weight. The weight of your body is your force felt by gravity. Divide that by 9.81, that'll give you the mass. So it depends on the problem. So what am I getting at? What is really important in this problem are units. The units themselves are really important. If you're given kilograms, that's a mass. If you're told an object has a certain amount of newtons, that's the object's weight. Okay? Weight is given in newtons, mass is given in kilograms. The same thing applies for the top formula. Let me discuss this one. So FF equals mu Fn. That formula is really useful, except sometimes students overuse it. And let me explain what I mean. If a problem tells you, what did you do? No, you did 84 in the problem set, right? With the girl with the sled, 84. The one after that was 85. It was a bird's eye view of a sled and 2 ropes attached to it, and it was pulled through the snow. In the example, the author says that there's a frictional force of, I don't know, say 20 newtons. If you're told the frictional force, what variable is that? If you're told that the frictional force is 20 newtons, what variable is frictional force? It's FF, directly FF, right? So if you're told, again, you're told that the force due to friction is 20 newtons, that replaces this whole thing right here. It replaces this whole thing right here. Now, if the problem said, find the coefficient of friction, what symbol is that? Mu. That's this symbol right here. So if you were given a frictional force, and you have this number, and you're trying to find mu, you would need Fn also. Now, this problem doesn't have Fn, so this wouldn't be the problem you've been doing now, obviously, right? There's no Fn in this problem because there's tension instead. But I want you to recognize that if I ask you on the test tomorrow, find the frictional force, it physically means solve for this variable. You don't have to replace it with mu Fn. You only have to replace this with mu Fn when you're looking for mu, or when you're given the mu value. So if I told you that the coefficient of static friction was 0.5, well, that's this mu value right here. If this is 0.5, and I can figure out Fn from the y direction, I can multiply those two to give me FF. So then it makes sense to replace FF with mu Fn and then plug in the correct numbers. So I want to point out the fact that we've done these problems enough by now to recognize that they're really the same for all problems. But there are some tweaks and little, not discrepancies, but little changes that we want to account for, and that's one of those things. We also want to consider the fact that not all problems are going to be applied at a horizontal or at a vertical. So let's go to the next slide to talk about that for a second. We've done this already. We've done this applying a force at an angle. So let's say that I am pushing on a piece of furniture. This is the example that we skipped, if you recall. It was two students like pushing on a couch. We ran out of time for this one, so we never got to it. It was like example 3 or 4, I forget. So let's take a look and think about that one. So here it is. Here's the example right here. Very simple. It's a garbage can, right? And I'm going to push it across the room. Which way am I pushing it? Left, right? Is that it? Just left? Look at my arm. Which way am I pushing it? Left and down. Very good, Alan. Left and down, actually. Whether or not I want to admit it, I am. Now, unless I literally got low to the ground and put my hand here and just like pushed, but I'd have to really push it like a perfect horizontal, which I really can't. So the minute I go to push this garbage can, I'm technically pushing it into the ground by pushing down, but I'm also pushing it to the leftward direction. So by pushing it down, what am I doing? I'm affecting its normal force. I'm affecting its normal force. And the normal force affects, oh, it's not here. The normal force affects the frictional force. Think about that again. I gave the example in class, remember? No friction, almost none, right? What do? Exactly. Take your hand, push down. You think, oh wait, why is there more friction? You're pushing down more, which increases the normal force pushing back. The more normal force, the more friction. That's why the formula for friction is friction equals mu Fn. Mu Fn. So in that scenario, let's draw a diagram of it. In that scenario, I'm applying a force like that. And I need to know the angle that I'm applying it at. Let's say that this force is called Fa for now, and we'll call this angle theta. What else is happening with this garbage can? So let's push it this way, by the way. Sorry, I'm drawing to the right. I apologize. So I'll take the garbage can, okay, and just push it this way, to the right, in the classroom. So the garbage can is the dot, right? The garbage can is the dot itself. Whatever object is the object of interest becomes our dot. So my arm is represented, or the applied force by my arm is represented by Fa. And I'm clearly pushing down at an angle. So take a look where I'm pointing here, please. Here's your angle right here. Okay? Between the horizontal, my shoulder pointing outward, and the vector, which is my arm, that's the angle theta right there. So the angle theta we're referring to is that in the diagram. So a problem like this, we have to consider the fact that this object is being applied a force at an angle, so it's both in the x and the y direction. So I'm going to start with a regular free body diagram. I'll draw my gravitational force acting down. I'll draw the normal force acting up. Which way is friction acting? Friction acting in this diagram. Opposing motion. Very good. So we're going to draw our frictional force a little bit different for this one. Okay? That's what it would look like. Again, if and sometimes, by the way, I haven't done this much in this class, but sometimes I tell students if they want to do this. Label the direction of motion. That could help. It could help. Okay? If it's like the track runner that's running this way, well, your static friction is helping you run this way. But if it's the garbage can that I'm sliding that way, it's opposing motion. So I want to keep track of the fact that friction usually opposes motion, unless we're talking about static friction, specifically static friction, where we have like a wheel rolling, or the shoes, the rubber between the rubber of your shoes and the ground itself. That frictional force that you step with is propelling you forward every time. My applied force is back. Friction is pushing me forward every time I step. And think about that logically. That's the only way walking works. If you were to try and walk on something that was frictionless, would it work? What would you be doing? This would be me walking on a frictionless surface. I'm not going anywhere. Okay, you see those examples in like cartoons where the character like starts to run, and there's like a little bit of a lag there. Where you ever see a car like slam the gas, the back wheels spin for a second, and then it finally grabs the ground and kicks off. What's happening there is that the rolling friction is not catching the ground, and the wheels start to like burn literally from the ground. And then eventually the wheels catch the ground and it pushes it forward. So in all problems that we're thinking about static friction to help our motion, pushing us, our static friction, we actually draw in the direction of motion the most. But for most of our problems we've done in this chapter, we've concerned ourselves with sliding friction here, or overcoming static friction. I'm pushing, it's not pushing enough. Static friction is pushing back until I get it to move, and now it's kinetic friction. All right, remember that idea? That was from that first lab you guys worked on. You pushed the object until you just got it to move. That was the maximum static friction it was given, right? The amount of force you need just to get it to move is the maximum static friction. What happened once it started moving?
There's less force coming against you when you start.
Yeah, the kinetic friction force, once it's moving, is far less than the static friction was present to keep it from moving. Remember, it's harder to get something moving than it is to keep it moving. Once you have something in motion, it's actually easier to keep it in motion. The friction of kinetic force, or the kinetic friction force, is always less than or equal to the static friction force, which is why this is also the case. Okay, those are both true. Always the case. The same materials, obviously. So, how many surfaces is friction a function of? How many surfaces is friction a function of? How many surfaces? This is rather straightforward. Use your common sense. Is? Why two?
Because the bottom of the garbage can and the floor.
Yeah. Friction is interaction, isn't it? Right? It's an interaction between two surfaces that are mated, that are actually adjacent or adjacent to one another. They're sharing some sort of plane. So you need two surfaces. So when you give a rating for friction, you can't just say, oh, the friction of glass is this. The friction of concrete is this. That doesn't make sense. You can't give a material property for this. It's the interaction between two materials. So for example, rubber, right, your shoe, rubber, on concrete is a pretty high friction force. Now concrete's also very cheap and there's other reasons we use it. But just walking around the city, when you walk, the idea is that you have grip on the ground. Sometimes though, you have less grip. When is that? When you have less grip when you're walking around? When it rains or snows. Because rain or snow acts as a fluid, which acts as a lubricant, which therefore decreases the amount of friction on that surface. So when we think about this, rubber on concrete is different than rubber on whatever this floor is, right? Like, look what I'm doing right now. You think I can do this outside on the street? Probably not, right? If I tried to do this on concrete, my feet would most likely get stuck. But there's very little friction between the rubber of my shoes and this floor. So I'm able to do that. I'm able to slide or shuffle across the room for that reason. Okay? So friction is a function of two different surfaces. Yeah? Yeah, of course. FA. How do I redraw my diagram now? That's one important part we're going to look at. So let's take the diagram we've got, which is in the top left, and let's go ahead and redraw it on the bottom in blue. And what I want to do is this. And what I want to do is I want to think about the fact that FA is applied in two directions and redraw FA with its components. I don't want to have to deal with data once I have gotten the diagram down. So I'd rather draw FA in two directions. Again, which way in my diagram here, right, in this object, I'm pushing it this way, take a look. Which way is FA applied in that scenario? Joe?
Down and to the right.
Down and to the right. I agree. So this is my FA in the x direction, and this is my FA in the y direction. And look what I'm doing already. I'm not even calling it FAX and FAY, because I think more and more students, when they see that, like, what is this extra subscript of x? It just means the FA and the x component. So just multiply by cosine theta. If you want the force applied to the y component, just multiply by sine theta. It is the same for every single problem. It never changes. Yep, absolutely. So Paula asked, can she put this FA on this side? Absolutely. Sure. Only reason I'm putting it on the left side is because my diagram, I showed it that way, but it's absolutely correct either way. Same with the friction force. The friction force that I'm about to draw, I'm going to draw acting to the left like that. But yes, you can absolutely draw friction on the left side acting to the left. It's the same thing. Normal force pushes up, and the weight of the object also pulls down. So that's my free body diagram that I'd rather use when I get into the math. Okay? The one at the top in black is like my standard free body diagram of actually what's happening. But if I'm looking at the math involved in this problem, it just makes more sense to use the one that's given in blue at the bottom there. It just makes life a little bit easier for us. Because everything is either horizontal or vertical now. Horizontal or vertical. If I were to write my equations of motion here, my equations of motion would look like the following. Same setup as always. Governing equation, same equation as always. This never changes right here, right? This never changes. And then I just fill in the blanks. What forces are acting to the right? Well, there's only one force acting to the right. Fa cosine theta. So Fa cosine theta becomes positive, right? And the only force acting to the left is friction. So friction becomes negative itself. And depending upon acceleration, we don't know what will happen there. But that's my x direction right there. And again, all I'm doing every time is drawing my free body diagram, making everything either horizontal or vertical on purpose. So then I can look at the horizontal and say, well, it's just these two. They're battling it out, right? It's tug of war. They're battling out. Those are the two forces right there. And then in the y direction, this time I've got three different forces. I've got Fn pushing up. I've got the weight of the object pulling down. And I've got the applied force acting down. And again, depending upon acceleration of this problem, I've got MAY or I don't have MAY. My diagram tells me everything. My free body diagram always tells me everything about the problem. Okay? Tells me everything here. Questions? No numbers there. Notice I didn't use any numbers at all. I just wanted to give ideas, theory of how we approach these problems. Now, based on the numbers that are given, we have to apply certain properties, right? So let's say in this problem, we're told that it is, I'll put these points at the top. I'll use red. So we're told three things. One, we're told that it's moving with a constant velocity. Two, actually, instead of constant velocity, we do that too often. Let's do accelerated motion for this one. Sorry, I apologize. Let's say that we're told, or no, you know what? Let's say that we're looking for the acceleration. So we're looking for the acceleration. We're told that the mu k value between the floor and the garbage can is 0.3, rather low, which it is. And we're told that the weight of the object is equal to 35 newtons. So we're told the weight of the object is 35 newtons. The mu k value is 0.3. We need an applied force also. The applied force itself is 38 newtons at 20 degrees, okay? Southeast, technically. Southeast. So the applied force is 38 newtons. The angle is 20 degrees, south of east, which is what's drawn in my diagram. The weight is 35 newtons. The mu k is 0.3, and we're trying to find the acceleration. So, first of all, for all these problems that involve horizontal motion, we make that assumption that I talked about, that it's not going to lift off the ground. But in this case, we know it will lift off the ground, right? Take a look at the garbage can. If I pull this way, look at the front. It might lift off the ground. The front physically lifts off if I'm pulling up, because I'm pulling up in this way, right? But if I were pushing like this, there's pretty much no way the front's lifting off the ground. Because I'm not only pushing it, but I'm pushing down, which keeps it on the ground. So for a problem like this, we don't have to consider the fact that it could lift off the ground. Okay, but we're making an assumption that it's not going to anyway. So if it's not lifting off the ground, what's the first thing I say? It's not lifting off the ground at all. What's the first thing I can say?
AY is 0.
Good. AY is 0. So let's go ahead and drop that off. Now, a lot's going on in this problem. A lot is going on. What do I know directly that I can plug in right now? What do I know directly that I can plug in right now? Helen?
FA.
FA.
Sine and FA sine.
Very good. So let's start with that. So we got the 38 times the cosine of 20, which is its angle. And over here we have 38 times the sine of 20. So all I did so far is substitute in for the applied force and the angle that it's at. Agreed. Good job. What else? Somebody else. What else do I have here? What else is given in this problem? What else do we see? All right, we're just reading the writing in the top. That's all we're doing right now. Reading off the writing. Helen, what do you got for this one? FG is what value?
35.
Very good, Helen. Helen took a little while to think about that. I'm glad she did. The weight is given as 35. The weight is FG. It's not the mass. The weight is FG, that whole quantity. So this is 35. So this is a minus 35 right there. Remember, we were not given the mass in this problem, so we didn't have to do m times g to get the weight. If you were given the mass, then you would have to do mass times 9.81, and that's what will be your value for FG. But we are directly given the FG value in this problem. Remember that weight is called the force due to gravity. What else? What else? I have more. I don't have Fn. I'm going to leave that alone. So in the y direction, already look at the y direction, people. What's the only missing variable is Fn, right? So clearly we're going to solve for Fn in the y direction. We're going to evaluate Fn in the y direction. It's the only thing that's not there. So if some of you want to already figure out what that Fn is on your calculator, go ahead and just move those other two values over. How come Fn is going to play a role? Why would I bother finding Fn? Where does Fn come into play? Where does Fn come into play? What formula has Fn in it? One formula that has Fn in it.
Fx equals x times Fn.
Yeah, the force of friction. The force of friction, the formula for that is always, remember, is always mu times Fn. This is why. Take a look at this problem. It's very obvious if you look at the equations. It's not obvious if you look at this line right here. Once I replace FF with its corresponding formula, mu is given in the problem. It's at the top of the page. Fn we can get from the y direction. Mass we're going to have to figure out. And then therefore what can we do? We can solve for acceleration, which is our goal, to find acceleration. Why, or sorry, not why. When would I not be replacing this with this? When would I not replace this with this?
Are you solving for Fn?
If you're solving for
Oh.
F, if you're solving for
If
F,
you don't have Fn, or you
okay, if the problem doesn't, you're not able to find that number, you might not be able to, good. But what would you be given then, in that case? If you can't plug this in, you only have this right here, right? So if the problem, instead of giving you mu as 0.3, if the problem was rewritten and said the force of friction is 20 newtons, you literally just replace this with 20 newtons. There's no need to take the coefficient times Fn. So whenever you're given the force of friction directly, you're not going to need to use this formula. And therefore, you're not going to need Fn. And therefore, this side doesn't even matter in a problem where, again, I'll say it one more time, in a problem where you're given FF directly, or you're asked, as Joe said, to solve for FF, you're asked to find the force of friction, you don't need to replace it with this. And then look at the formula. There's no Fn involved in that formula if I don't make that replacement. There's no Fn anywhere in this formula right here. So therefore, the y direction is not very important unless I'm told about the mu value, or unless I'm looking for the mu value. So again, write yourself a note that when this is either given, if this is given, mu equals 0.3, or if you're looking for the mu value, that's when you're going to go ahead and replace ff with mu fn, and then that's when you're going to take fn from the y direction and plug that fn from the y direction into the x direction. Only for problems involving either finding mu or when you're given mu are you going to worry about the linking variable, about this fn moving over. So in this problem, because we're given mu, we can plug in 0.3 right there. Fn is whatever number this came out to be. Oh, what's the mass in this problem? What's the mass? That's the one thing we still don't have. So I'll jot down what we have here. We got 38 cos 20 minus 0.3. What was Fn? What did Fn turn out to be, Julia? 147.99? 47? Thank you. 47.99. So look at my formula in black. What am I missing? I'm missing just the mass now. If I can get the mass, I can get acceleration. Think about the goal of the problem. The goal is to find acceleration. So everything else must be known. Mu was known, Fn was known, but how do I get the mass? How do I get the mass, Joe?
Divide 47.99 by 1.8.
Careful, you're on the right track, but use the wrong number, Joe. You always divide the weight, right? The weight by 9.81.
So 35 by
Yeah. Remember, this is my formula here. Right? That's how I get mass. Because really, isn't Fg equal to mg? Isn't this g really up over here? Fg equals mg. Take the g and divide it to get mass by itself. We were given the weight of this object in the problem itself here, so we can plug in for the weight of 35 newtons and divide that weight by 9.81, and that'll give us a mass of around 4, a little bit less than 4, I'm sure. What do I get for a mass for this? What does the number turn out to be? 35 over 9.81? 3.57. And if it's mass, what are my units there, Joe? It's the only one that's not a base unit. It's kilograms. Kilograms, yeah. Remember, this is the exception I was talking about. Every other unit, like meters, is given as meters. Seconds is given as seconds. But mass is always given not as grams, but as kilograms. So we go ahead and take that value of 3.57. Oops. Take that quantity, 3.57, and go ahead and plug it in all the way over here for mass. And then we can solve for acceleration in the problem. So what looks like a really complex problem, especially like on day 1 when we did this with section 5.2 in the very beginning, this seemed really elaborate. But if you think about the approach to every problem being the same, which they are, every problem's approach is always start with this line here. Start with this line here. Replace your forces. Replace your forces. If your acceleration doesn't exist, set it equal to 0. If you're looking for acceleration or if it's given, you leave it there. And in this case, we were looking for acceleration, so we're going to solve for AX. So the approach to each problem is really quite generic. It's not going to change on your test. Here's one thing I would consider tonight when you're studying. First of all, under documents and handouts, I put 4 example problems, like pulling at an angle and stuff. 4 practice problems, good to look at. You have homework from 5.3 tonight, but don't forget about section 5.2. 5.2 is the easier section, but students have a tendency to only focus on 5.3. 5.2 is like if you lift an object off the table, or if it's an elevator problem moving up and down. Those are definitely fair game and a good problem to study. Okay? All right, I'll see you guys tomorrow.